On proper integrals, we've already discussed that, correct me if I'm wrong, class, we've already discussed that they may be improper because they have this infinite limit in their integration. So you either have the infinite limit on the upper limit, or you can have the infinite limit in the lower limit. Or the type 2 is when there's a discontinuity in the graph of your function on the indicated limit of integration. Or we also refer to this as the interval. We call this as the interval. What does this mean? That if I will plot 1 over x squared, it will have a point of discontinuity on the values -1 to 1. If I recall it right, I've plotted this one and I've shown to you that at x equal to 0, this particular function will be asymptotic to the vertical axis, approaching it upward and downward separately, depending on which part of the x-axis is it coming from. If it's coming from the left side, it will be approaching it upwards, or downwards rather, but if it's coming on the right side, it will be approaching upwards. So your function is having a discontinuity, even though you see that the limits are not infinite. So if your function has a discontinuity on the indicated limits or interval of integration, the said function is also named as improper. So the integral of such a function is also an improper integral. So they will only come in two forms: the one that has an infinite limit and the one that has a discontinuity on the limit of integration. Okay? Now, so definition. So you have an infinite limit here. Now, this is equivalent to saying that you will evaluate the integral as t approaches infinity. So you notice that the infinity here was changed to t. So it's just like taking this integral with the limit that t approaches infinity. This one is also an improper integral. Now, this one is also improper because your lower limit is negative infinity. This one is improper because your upper limit is infinity or positive infinity. Now, this one has an equivalent expression of an integral which has an upper limit of b but a lower limit of t, but this t approaches negative infinity. So this is also improper integral because one of the limits of integration is infinity. The other one is this: both limits, the lower limit and the upper limit, are all infinity. If that is the case, class, you are also given an improper integral. So these three are actually all improper integrals. So this one is equivalent to two separate integrals. You look at it. So you can have negative infinity to a here in the first integral, same function of x. But since you ended here with an upper limit of a, that becomes the lower limit of the next integral of this same function, but this time the upper limit is infinity. So if you add these two, it's just like having one integral having a limit of negative infinity to infinity. So both, or rather three of these, are all said to be improper because they have limits of integration which have infinity. Now, what about type 1? So the previous ones are all type 1. So if we have the curve y equal to 1 over x squared, so if you're going to, let me just accept class, those who are waiting. So if we are going to plot this particular curve, this is the curve class, okay? And above the x-axis, you could see that the area of the curve is this shaded portion, okay? The curve, however, that we're talking about is this one, this pink curve here. Okay, that's the curve, or this is the plot rather of 1 over x squared. So if you're going to plot it to the right of the line x equal to 1, this is your line x equal to 1, this line class. So if I will extend it, it's the x equal to 1. This would be the area that will be under the curve. The area is 1 minus 1 over t, depending on what's the t in here. Okay? Depending on what would be the t that we will have in here. As t increases, this one, as t increases, the value of 1 over t become very negligible. Sa aton language, sa vernacular, kung ginadako ko ni si t bala, meaning to is, for example, diri abi 4, diri 10, or 12, nagadako ni siya, this one increases, the value of this decreases. It's just like you're subtracting from 1 a value that is very negligible compared to it, because as this one goes big, the entire value of 1 over t becomes small. So it's like the area under the curve is just like equal to 1 because this one is very negligible in value. Okay, now let me continue. Now, if you might think that since S is infinite in extent because its area must be infinite in the sense class nga ti wala man ni katapusan ang t niho, kay sige man niya increase ang t dira. However, let's take a closer look. So the area of the part of S that lies to the left of the line x equal to t is shaded. So this is the shaded part. Notice that as a of t becomes lesser than 1, no matter how large t is chosen. So your area, this area is less than 1 no matter how large t is chosen. Because if we go back here, no matter how large this is, no matter how small this is, this value of the area will always be less than 1 because you are subtracting a value from 1, which is 1 over t. This is what I'm trying to say here in this part. So then we say that the limit of 1 minus 1 over t as t approaches infinity is equal to 1. So this value actually, if we increase t, will always be lesser than 1, but as t approaches infinity, the value is equal to 1. It approaches a value which is very close to 1. I think I have explained also a while ago, kinilunggo ko pa nga, kung padakuon ko ni siya, nagagamay ni siya. Kung nagagamay ni siya, it's as if you are subtracting a very small value from 1. So as we increase t, this is what it meant here, as t approaches infinity, the limit of this entire expression is just equal to 1. So if that is the case, since the limit approaches a particular value, which is not infinity, your function is said to be, ang terms na may duwa kita ka terms later on, natunan, which is the convergent and the divergent function. So let me show to you this one. So this is 1/2. If t is 3, you have 2/3, because 1/2 minus 1/3, that would be 2/3. If t is 5, that would be 1 minus 1/5, so that would be 4/5. If t is very, very small, the area is equal to 1. So, amo ni siyang ginanamin nga as t approaches infinity, this area value approaches 1. Because if t is big, this one is small. O, ginapadako ta siya, ang t naton, nagadako ang area. Pero kung dako siya, nagagamay ang area, ang iya sina nga relationship is inversely proportional. In our in chemistry, you might have heard that already being used by your teacher. Inversely proportional sila. If I increase the value of t in this case, the area in this case is increasing. But the value of the t is also increasing. So in this case, directly proportional sila. Okay, I stand corrected. Directly proportional because as we increase the t, the area that you have here is also increasing, making the 1 over t value very negligible to 1 when it is being subtracted. Now, I'll just move forward. So we say that the area of the infinite region S is equal to 1 as we write it in this manner. So your limit is from 1 to infinity. Balik ko ha. Nga amis 1 to infinity, kay ini siya ho, ining t ni 2 di siya, diri 3 di siya, diri 5 siya, diri wala na naka-indicate. I'll move it even backward. This t is this t here. So meaning it's going to continuously increase in that sense. That is why here you could see that it's from 1 to infinity. We started with the line x equal to 1. This is your line x equal to 1. Ini sila. And up to t equal to infinity. So the value is equal to 1. Using this example as a guide, we define the integral of f, not necessarily a positive function, over an infinite interval as the limit of integrals over finite intervals. So, how do I say this I will say this in Ilonggo. Ang isa ka integral nga ginbutangan mo sang limit nga infinity, ginbutang mo siya subong sa integral nga defined. Di more or less defined siya, okay, 1 to t, but ina siya nga t ga approach infinity were interpreted as a limit. That way we can interpret this one as equal to 1. Now it has a definite value. So the integral, shall we say, of 1 over x squared from 1 to infinity is more or less equal to 1 because it's equivalent to the integral of 1 over x squared evaluated from 1 to t as t approaches infinity. So this is the interpretation. The one that you have here on the right is an interpretation of this one on the left. Now, you may wonder why. Why need to interpret an integral with an infinite limit in this manner? Why do you think? If you're going to process this class, just like any integral, so you will have 1 over x squared. If you integrate it, the integral would be x raised to negative 1 over negative 1. So that would be negative 1 over x, right? Now, if you're going to process it and you apply 1 over infinity, the answer would actually be still equal to 1. Because your upper limit would be 1, your lower limit would be, rather your first term would be 1, but your second term would be 1 over infinity. 1 over infinity or anything divided by infinity is 0. So 1 minus 0 is still equal to 1. Now, what do I mean? What do you mean by that, Miss Ali? I'll annotate here. Your answer here will be actually negative 1 over x. Your limit is 1 to infinity, right? When you integrate this one. Now, if you will apply what we have learned in definite integral, this would be 1 over 1. I substitute, or rather 1 over infinity in this case, because upper limit is infinity, minus 1 over 1. I can see that. Now, this one, 1 over infinity is 0. So this is negative of negative 1. So that would still be 1. And it's the same as this one. Okay? This is just an interpretation. This one, the limit thing, is just an interpretation of your improper integral on the left. Okay? Now, I will just clear the drawings here and proceed because there are 2 people who needs to be admitted. Okay, now we move on. Now, this is type 1, case 1a. If your integral having a limit of a to t exists for every number of t, which is equal or greater than a, as long as this t is equal or greater than a, then the integral of a to infinity is equivalent to this interpretation, the one that was provided to you a while ago, provided that this limit exists as a finite number. Isimplihon ko na siya, class. Anong namin sinid that provided this limit exists as a finite number, meaning you will have a definite answer for this integral, just like the one that I have mentioned in the previous slide. Okay, that's type 1, improper integral type 1, or the case 1a. Now, what about the case 1b? So in here, your limit, your infinite limit is the lower limit. And you have here t as the lower limit, but that t is approaching infinity. Or specifically, class, there's a typo error here, negative infinity. Again, provided that your answer for such an integral will be a finite number, not infinity. Next is this one. So you have this and this. These are improper integrals and they are called, so I mentioned the term convergent and divergent a while ago. So they are convergent integrals, or improper integrals are convergent integrals if the corresponding limit exists. When do we say that the corresponding limit exists? When you have a finite answer, you have a real number answer if you will evaluate your given integral. Otherwise, if the limit does not exist, then the said integral is divergent. So we say it will exist. It will exist if the answer is a real number. It does not exist when, of course, your answer is infinity or negative infinity. So take note of the terms convergent and divergent. Now, what about case 1C? Case 1C, amo ni siyang ginhambal ko nga ang imo limit sang integral hindi infinity. Okay? Or rather, ang imo limit sa integral hindi infinity, but rather the limits of your integral are both infinity. Sa case 1A and sa case 1B, only one of your limits of integration is infinity. But in here, you have already both limits as infinity. So you have your negative infinity and positive infinity. Here, any real number A can be used as upper limit for the first integral and lower limit for the next integral. This is still improper integral, case 1C. So case 1 because type 1 sila. Ang type 2, di ba, amo to ang may discontinuity. So amo na siyang dasuntang istoryahan. So either the limit of integration is upper limit, lower limit, or both limits being infinity, we have an improper integral. They are said to be convergent if the limit exists, meaning you have a real number answer. Otherwise, it is said to be divergent, meaning your answer is infinity or negative infinity for the said integral. Now, example. So, determine whether the integral 1 over x dx from 1 to infinity is convergent or divergent. So, you will only know this if you are able to answer already this particular integral. Convergent if we will have a real finite answer. Divergent if we will not have an answer. So, let's see. So, case 1A, you will have to evaluate it from 1 to t and evaluate the limit as t approaches infinity. So, the integral of this you've learned already will be ln of x. And if you substitute the limit of integration 1 to t, that would be ln of t, the upper limit, minus the ln of 1, here, the lower limit. ln of 1, so ln of 1 is 0. But ln of t, as t approaches infinity, is infinity. Again, I will annotate here. The ln of 1 here is 0. But the ln of t, it's like you will substitute here ln of infinity because you will have a t value which is approaching infinity. So the ln of infinity, class, is infinity. Now, since the limit does not exist and is not a finite number, your integral is divergent. This is case 1 because your upper limit is infinity. Okay? Case 1, type 1, divergent. Now, we'll continue. Wait, class. Where is it? Okay, we'll proceed. So let's go. Okay, what about if we do by parts for this particular integral? Okay, example 2. So you have integral of x e raised to x. And if you will integrate this will require by parts because you have two different functions, exponential and algebraic function in here. Okay, so when you process the by parts using the uv minus v du formula, this would be your first term and this would be your second term. If you will substitute your limit here, t to 0, this is actually your answer. You have minus t e raised to t. Now specifically, I will annotate again. For the first part, when you substitute the limit here, I will place it in here, you will have 0 e raised to 0. You substitute for the x, the zeros, minus then the t for the x, so t e raised to t. That would be for this term here. For this integral, your answer would be simply e raised to x. And the limit is from t to 0. And then I will place here minus. So if you will substitute the 0 here, that would be e raised to 0. And if you substitute the t for the x, that would be e raised to t. Okay. Now, that's the answer that you have here. You have negative t e raised to t. This one is equal to 1. So minus 1 plus, because minus minus, e raised to t. Okay. Now, somebody needs to be admitted. Gio. Now, if you have this now, this is your final answer. What's the next thing that will happen? So there's a need for me to erase what I have written here. Cannot find my... Okay, we'll proceed. I cannot. Now, what about this? Example 2. Start talking about example 2. This one. And you have this. This is for t to 0. What about if it's infinity already? Okay. We know that e raised to t is 0 as t approaches negative infinity. And by L'Hopital's rule, we have that the limit of t e raised to t as t approaches negative infinity would be, it's written like this, class, t over e raised to negative t. This one that is having a positive exponent is written as a denominator. Now, it would be 1 over negative e raised to negative t. Wait, now why may 1 na siya? Should it be as t approaches negative infinity? Okay, now I understand. Why do you think this one is the answer already? Why do you have a 1 over negative 1 e raised to t? From the limit of t e raised to negative t, you have now a 1 over negative e raised to negative t. Why do you think we have this? Anybody in the class? Was it discussed in your differential calculus? What is L'Hopital's rule? We pronounce this as L'Hopital's rule. Hello? Are you all there? Class, are you still there? I have 35 students, but nobody is answering. Was L'Hopital's rule discussed in your calculus? Or you can answer in the chat box, because I cannot proceed unless you know L'Hopital's rule.
Yes, miss.
Oh, so I was asking, do you know how this came from, or how this become from this one?
Gin-derived na lang siya, miss.
Oh, gin-derived siya. So, iban wala. Thank you for that. So, if you derive, this would be 1, and this would be negative, because this is EU. If you derive that, that would be EU du. The du here is negative 1. So, you have negative e raised to negative t. If t approaches negative infinity, class, by the way, I'll write something here for you. I think this was mentioned also in your calculus then, but I'd like to write it here. Your e raised to negative infinity is 0, but your e raised to positive infinity is infinity. Okay? So in this case, if you evaluate the limit, so this one was written in this form. That way, it would be easy for you to apply L'Hopital's rule. L'Hopital's rule is applied to rational expression. When you speak to rational expression, may numerator siya class, tag may denominator. What we do is we differentiate separately the numerator and the denominator. And after that, apply the necessary value in which the variable in your limit is approaching 2. In this case, it's negative infinity. So this one has an answer equal to 1 over negative e raised to negative infinity. So this would be a 0, negative e. Notice what it was done here. Oh. This is, halin siya sa negative, ginubra naman siya positive para lang hindi siya mag-determinate. So from the denominator, it was written here. That way it could be written in this manner. Now this limit now, or we take away the limit, this limit now is negative e raised to t is approaching negative infinity, and that is why you have here a 0. So from the original, notice on how it was manipulated. That way, from a rather indeterminate expression, we were able to find a finite answer, which is 0. So you have from this to this form, to this using L'Hopital's rule, and from this, it was returned back into the non-rational form, which is having a positive exponent. That way, you can substitute this one. Anyway, if you did not alter it, like it's really written as this one, your answer here will be 1 over negative e raised to negative of negative infinity. This one would be e raised to infinity, positive infinity, and that would be this one, infinity. 1 over infinity would still be a 0. So it doesn't matter whether you convert it in this form or right away you substitute the negative infinity here, you will still have an answer which is equal to 0. That is if in our second example, your t approaches negative infinity. I will clear what I have written here. Before I will clear anything here, do you have any question before I can go back to the previous slide to point out something? None, so I will erase everything here. So this is in the case wherein the t that you have in this expression here, exponential expression, is approaching a value which is negative infinity. So we'll proceed. So therefore, if you have a limit for negative infinity to 0, for our t in the previous integral, this is our previous integral by the way, this t. If we will change that to negative infinity like this one, which uses this discussion here, it would be like this. So negative t e raised to t minus 1 plus e raised to t. Now, the value, if you substitute negative infinity to all the t's would be, so you have in this one, I have trouble writing. You have here in this one negative of negative infinity e raised to negative infinity for this one. This should have been, class, this should have been indeterminate. This should have been indeterminate. However, hindi ko na pag-erase, mabalik lang ko dire sa pihak ha. That's the one that we have discussed here. This is the one that we have discussed here. The limit of t e raised to t as t approaches negative infinity. That's the one that we have discussed previously before we substitute the answer here. Our answer in the previous slide, which is 0, was placed in here. This one is what we call in your differential calculus as indeterminate. So we need to find its value, its actual value, because we cannot answer when we have an indeterminate term. So this is indeterminate, this one. So the reason why you have the previous discussion in the previous slide is to answer this. Now this one is negative 1, and you will have e raised to negative infinity here, which is a 0. Now, it ends up with an answer which is a real number, a -1. So this type 1, case 2, improper integral, type 1 because one of the limits of integration is infinity, type 2 because it's the lower limit that is infinity, is convergent. It is convergent because the answer is -1. So the process that we did here in the previous slide, in here, this one is for us to be able to determine the indeterminate value, which is this, ini siya. Because you need to evaluate this particular term of the limit negative t approaching infinity. For this integral here, where t is approaching negative infinity. So actually, this one is the integral from t to 0 when the limit is t approaching negative infinity. So prior to having the third slide after this, we already determined this one. What is this indeterminate form? That way we can simply plug in our answer in here. So it is convergent because, as I said, you have a real number. You have a finite number answer to your improper integral. Now, I will have to erase this one because you will not understand everything here if I will not erase. Okay, so this is example 3. Both limits are infinite. So type 1, case 3. So it's convenient to choose A equal to 0 in case 1C. This is case 1C. All the limits of integration being equal to infinity. Now you may wonder why. Why, miss, of all number is A? The A, isn't this A when we split this one into two integrals? This is A. And it was assigned a value of 0. So you may wonder, why 0 of all number? Why not 10? Why not 20? Why not -2? Why 0? Anybody here who knows why is it really 0 that is placed in here? Although it could be any number. Why is 0 chosen here? It could be 10 actually. It could be 10 here. It could be -5. It could be -5 in here.
Ay,
Okay. Yes.
asymptotic sa zero.
Yes.
Ay, asymptotic siya sa zero.
Asymptotic siya sa 0. Okay. Now, let's say, for example, thank you for that. If you don't have any idea about being asymptotic, now, if you're going to substitute a 0 here, would it be asymptotic? So, I'll place here a 0 value, negative infinity to infinity. Will it be asymptotic to 0? This one? 1
So,
over 1 plus x squared. Asymptotic siya sa 0. Ang function.
hindi, siguro, miss.
Hindi. So, true lang to siya ihot sa answer kay sa aton nga function no 1 over x squared. Kay asymptotic siya sa 0, pero hindi siya asymptotic sa 0. Although your answer that YA was substituted, or y is 0 substituted for a here, it's because it could be done really for functions which are asymptotic at 0. You can place a at 0. But in this case, sa sining a specific example, hindi siya asymptotic sa 0, ha? Kaya magsiling ta asymptotic sa 0, wala ni siya value, ma-discontinuous ang function. Diriya may value siya. Kung i-substitute nyo di 0, 1 ang aton function. So, hindi siya asymptotic. Okay. Pili lang man na di siya nga 0. I'm again using the Ilonggo para kaintindi. Pili man lang na siya 0. Kaya magsiling ta negative infinity. Kag positive infinity, your function is decreasing infinitely if it is in negative infinity. This one is increasing infinitely. And somewhere in the middle is 0. So that is why 0 was assigned to A. But it could be any number, not necessarily 0. Convenient lang. So it's just convenient to use A being equal to 0. So this is type 1, case C. Okay? The case C conception. So if you will evaluate class, if you will evaluate this 0 to t where t approaches infinity, This one, of course, you know how the integral will be. It's an arctan of x. And if you substitute t, which is infinity, and t, which is rather x, which is t, and x, which is 0, your answer for arctan of 0 is 0. But when you answer for an angle in which your tangent is infinity, that would be the 90-degree angle. You check in your calculator. If you press tangent of 90 degrees, that's pi over 2, the answer is infinity. So we're looking for that angle. When you are looking for the arctan, actually you're looking for the radian value of the angle, which is infinity. And that angle is equal to pi over 2. Okay? Now, this same thing, you do it in here, but this time, it's your lower limit, which is negative infinity. Your upper limit is 0. So, you still evaluate and then substitute for the x, the 0, and t. This would still be 0. This one would still be 0. And the angle that will yield a tangent, which is infinity, is negative pi over 2. Okay, in this case, an arctan of, or a negative, shall I say, a negative infinity is a negative 90 degrees. Negative infinity, class in the sense nga ato siya sa dalom sang imo nga x-axis ang imo nga opposite side. The opposite side is below the x-axis. Rather, the adjacent side, not the opposite side. Because when we speak of tangent, is opposite over the adjacent. The adjacent side of your angle for negative 90 degrees is 0. You don't have. So that is why it's negative infinity. So negative pi over 2. So this is pi over 2 for this one. And this is pi over 2 for this one. If you subtract the two, the answer is, wait, rather we're not subtracting, but we're adding. We're adding the two. I stand corrected. So your answer would be a pi. But before I go back to that, do you have any question to this? Answers here. So remember, when you're finding for the arctan, the arcsine, the arccosine, you're looking for the radian value of the angle. You don't answer here 90 degrees. You answer in radian. So that would be pi over 2. In here, that would also be pi over 2. These two, by the way, the sum of these two, by the way, is equivalent to our original integral, which is having the limits negative infinity to infinity. And we're adding, we're not subtracting. So since you're adding, if you add the two, the answer is a pi. So for this type 1, case C, type of improper integral, we have a convergent improper integral because the value of this is actually a pi. That's the value, a pi. Okay? So type 1, case C, type 1, case 1C, and it is convergent. So both integrals are convergent. The resulting answer is real, so it is convergent. Now, what about type 2? So these are actually, shall we say, integrals, which if you look at it, class, it's so easy to really make a mistake. You will easily say it's not an improper integral because the limits are real numbers. But if you really look intently and you check whether there will be a discontinuity in the graph of the function based on the interval of your limits of integration, then you will know that it's an improper integral. So this is where most of the students actually make a mistake based on experience. It's so easy to say it's a proper integral or it's a simple integral because the limits are all real number. But you have to be careful because even if they are real numbers, but if when you plot your function, it has a discontinuity on the limit of integration, then it's an improper integral. And that's under type 2. Now we will discuss this, or I will have this recorded. That way you will not anymore discuss this next Monday after the Holy Week because this one is really detailed, a detailed set of slides for improper integrals and the convergence and divergence of the two. It's almost time and I may be using your time again for your next class. Okay. I will have this recorded, this last part for type 2 and the different cases under type 2, and will all post it in your Canvas. So please, from time to time, check what is available in your Canvas. But for now, do you have any question? I still have 3 minutes. Do you have any questions here on the previous examples discussed before we part ways for this afternoon? Have any questions? Especially here, and especially in the part of the L'Hopital's rule, the use of the L'Hopital's rule. By the way, class, the L'Hopital's rule is being used for indeterminate expressions. We find for their exact value using L'Hopital's rule and other techniques that your teachers then might have helped you use. So it's not only L'Hopital's rule that evaluate indeterminate forms. There's still a lot of techniques aside from this one. Any question? I may take time to post the recordings because there is really something wrong with PLDT connection. It's so good that in our class I was not disconnected. It has been days that PLDT has not been really giving good stable internet connections here in my place. So no more questions, class. Everything is clear. Don't hesitate to ask me questions even in private message, as long as it's not off office hours. Okay, especially in this topic, because the other topics are relatable, but improper integrals really is not so relatable with some of my students or a lot of my students before. Okay, so I'll stop sharing for now. I'll take again attendance. 34. So okay. Okay, no more question, class. Okay, so bye for now. Stop recording.